And life learning on her own through repetition and trial and error. The teacher learned that Anne wasn't just different, she was gifted. Anne needed to learn in her own way. And if she didn't succeed at first, Anne didn't mind at all. She'd simply have to try and 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 try.
Okay, so throughout this tutorial, I want you all to keep the story of Anne, how she is learning on her own, and how she, so how she's learning on her own, and this iteration process that the video talked about. Right. So initial question, even why deep learning, right? So this might not be a very good picture, but I think it gives us an initial description of where to start. So if we take a look at older machine learning algorithms, as the amount of data, for example, if we take random forest or decision trees, as the amount of data increases, after some point, the performance actually plateaus, right? Or we reach a certain point where decisions are really deterministic, and the performance of that algorithm can't improve anymore. But in deep learning, that's not the case. As the amount of data actually increases, performance increases as well. And we'll see that as we go along. So there are a lot of practical applications that are now in real life, and that's all of us actually use every day. Some of those are virtual assistants like Siri, Google Assistant, Alexa. All of them are have neural network architectures behind them, powering them. And also entertainment, recommendation systems, the YouTube algorithms that actually power off what you actually see. Netflix recommendations, Amazon shopping recommendations, Spotify music recommendations, everything is these days powered by deep learning, especially. So, and in the entertainment industry, it has really made a huge impact. Yeah, and also another practical application that we can think of are news aggregation and fake news detection websites, right? So again, sort of like a recommendation system could be where, of course, you and I would not really have similar preferences to the news that we'd like to have. Someone in one country would be interested to know about the specific local cases that are happening, but someone elsewhere might not really find that information relevant. Yeah, so, and also to detect fake news before it spreads. So different social medias can use this deep learning techniques to detect whether or not even a tweet, a post contains illegitimate information. So fake news detection is also one aspect where deep learning can really shine, right? So we've talked about why we use deep learning and some of the aspects of deep learning. But before we really dive deep into deep learning as well, let's go back and talk about what neural networks are, right? So here on the screen, what you see are brain neurons. Like most of the technological advancements that happen, for example, like advancements in cars, neural network architectures were also based on the basis of our bodies, on the basis of our brains, which are these neurons. So what you see here are connections of neurons, right? Connections of neurons where signals are being transmitted to each other. And so that biological entity where signal transmission occurs until it reaches a specific nerve ending where maybe a response is required, that is actually the basis of deep learning. So yeah, so those are neural networks. So what a neural network architecture in our concept, going back out of biology, this is a neural network architecture, right? So don't get intimidated by this. So we have a specific input. So you can think of this as just the neurons of our brains, which are carrying information from a specific input. For example, could be from the vision that we're seeing from our eyes. This could be like a specific perception. You can think of this input as that perception, and this transmission of those of what we just saw passing through specific neurons of our body, so that we are able to then have some output, right? Might be like reading it out loud if it's a text that we're seeing, might be to close our eyes if it's dust that is coming our way, and just like that. So that brain architecture is actually implemented here over on the deep learning aspect as well. So we have specific inputs, we have neurons. The specific term for neurons in this case changed to perceptrons, but you can call them neurons as well. And so, yeah, it's just that biological flow going on to be implemented on the computer science side as well. And so this slide will be shared. This is a really good introductory video on YouTube that you can watch later on. So let me go to the next slide. Yeah. So we've talked about what neural networks are. So let's talk about deep learning right now. So what is deep learning, right? A deep learning algorithm, it is an algorithm which is able to learn hidden patterns from the data by itself, right? So that specific architecture that you saw is using a deep learning algorithm, and it learns those hidden patterns by itself. So it does not need any human supervision. we should take note here that it is still mostly used for supervised learning, but it does not use it does not need any human supervision. And and we build much more efficient decision rules using deep learning, right? So what does it mean to learn hidden patterns, right? So going back to the architecture that we had previously, right? We have an input and we have some specific output. So how a deep neural network actually works is there is that specific input, and you have some layers of neurons, right? And each specific layer is actually tasked with doing a specific thing, right? So you have your initial raw input, and after that, the next layer would then be tasked with doing some more or less small tasks like detecting edges of the face. For example, in this case, it's let's say we're building a face recognition system, which is able to take attendance automatically, right? So if you have employees and you want to keep track of them, and you want to build an attendance system, and you want to automate the recording of attendance, you can use deep learning. Like, deep learning is a very great example of that for such system. So you'd have this layers of neurons or perceptrons. I'm going to use neurons from now on. So you'd have this layers which have multiple neurons in them, and so the first one would detect those specific edges, and the next one would detect more relevant or more advanced features, and as it goes on. And the output layer, for example, if let's say you have 4 employees that you want to keep track of, so it would take those faces and it would maybe then classify, say this is maybe employee number 1, this is employee number 2, this is employee number 3, this is employee number 4, right? And based on some certain confidence level that it has assigned. So for example, it might be very, very confident that this is employee number 1. The image that it is actually seeing is employee number 1, and it might be like, it's probably not employee number 2, it's probably not this as well. And also probably not employee number 4, or there may be some mismatch depending on how accurate our model is, or how similar the faces that the model is seeing. So that is one aspect, and again, another example of the use of deep learning. Yeah, we've been seeing different machine learning algorithms, and we've been talking about machine learning in detail. Is it a question? Yeah. No, it's not a single layer. So layers, this is a single layer, right? So a perceptron is this single circuit. So sort of like that single neuron that we saw here. So this is a layer. This single one is a perceptron. Okay, so machine learning versus deep learning, right? We've been seeing lots of machine learning algorithms, but deep learning is technically just a subset of machine learning, right? It's at the moment, at least, just fancier image, and machine learning is also a subset of artificial intelligence. Yeah, so again, on the course of machine learning versus deep learning, so feature extraction is the process. We've been trying to extract useful features and build machine learning algorithms thus far on previous weeks. But this is really where deep learning really shines, right? It's able to really encapsulate this feature extraction process. And so this really cumbersome manual process of where you'd have to extract specific features and feed it into your machine learning algorithm deep learning really eases that process. You'd still definitely have to do specific feature engineering, but this goes back to the initial image we saw where deep learning really performs well on as the data increases, right? So when you have like petabytes of data to train your model on, really feature extraction would be really hard. So deep learning can really analyze those features itself, given enough time and tuning of that algorithm. So why is deep learning so hot right now? Right. So one of the biggest reasons is really the data growth that we've been seeing, right? So this is associated with the social media boom, where everyone is really sharing so much data at the moment, and also where every business decision is really data based, right? You're not gonna use a hunch to decide any sort of business decisions from now on. So everything is data based, and this huge data growth has really promoted the boom of deep learning. Another reason is hardware advancements. You can look into how GPUs are used and TPUs, also the tensor processing unit that Google has made. And this really increase in the hardware capacity has also really helped deep learning, because deep learning is really computationally intensive, and so it requires good hardware, and so also cloud computing, right? So right now it's not necessary to actually buy racks of hardware at the moment, right? With just in a minute or two, you can spin up like large instances and pay by the hour for computers that would cost thousands of dollars to actually buy. So you have access to that amount of compute instantly at your fingertips at the moment. And I think another factor is the AI boom, which is really the hype. So people just want to do what other people are doing. That's just how we work. And so in real life, you'd see like many things like don't even require machine learning, let alone deep learning. But yeah, since everyone is doing it, the other people who are not doing it want to do it. And so there is this great article that is linked below. You can take a look at that later on. Okay, so the three pillars of deep learning. From a perspective that you view it on, there are definitely going to be multiple pillars, but so let's look at what I'm considering right now to be three of the pillars in your neural network architecture, or while you're doing deep learning. So these are forward propagation, backward propagation, and gradient descent. Right, so let's look at forward and backward propagation together. So what we've said is we have specific inputs. We have some hidden nodes. We have some nodes, which are those perceptrons that we've talked about. And we have a specific output that we're classifying, right? So everything is numeric. Like, let's think of it, everything as numeric. So there is some numeric input, and this specific connection as well, like there is also some number that is assigned here. And actually we'll get to that later. So just forward propagation means the input flowing this direction, like in the forward direction, right? From the input to the output. And backward propagation is the process of where the neural network actually goes back, right? So it went from the input to the output, and from the output or prediction, the process of going back. And we'll see the use of this going forward and backward in time process later on. So So there is again backward propagation calculus for those who want to dive deep into the uses, dive deep into how backward propagation actually works underneath, so the calculations that it uses. So another pillar is gradient descent. So what gradient descent is technically is just an optimization algorithm, which is used to minimize the errors between predicted and actual results, right? So I'm not completely sure. Okay, so I think let's go back to this and clear everything up right here. Okay, so there are, how this works is you have specific inputs which are numeric values, right? And there is this connection between each of the layers in our architecture. So there is disconnection, there is disconnection, there is disconnection, there is disconnection. So what this is called is actually a fully connected neural network, because each of the nodes that you see are actually connected with each other, right? So each of the nodes actually have their own specific values, right? So for example, if we think of these features as columns, they would have some values. Like for example, in the case of your price prediction system, let's say this is the type of store, right? So this is type of store, let's say 1, and this is also this is the district of where it's located, and this is given a numeric value of 59 and so on. So there is this numeric value that is being inputted, and this connection also has some numeric value which is called the weight, right? And there is some specific weight that is assigned to each of the lines here, to each of the connections. So there is also weights that are assigned to each of the connections here. There is weights that are assigned to each of the connections here, right? And each of the preceding nodes also have their own value, right? And they get this value from the weighted sum of the previous connections. So what the value of this would be in our case would be like, there is a specific value that is here, and there is a specific value that is given to this line. And so the weighted sum would be like this times this plus this, the value of this times this, the value of this times this, the value of this times this. And you would sum each of this up together. So you'd sum up all of the values that we get by multiplying these values, and you'd apply some function, which is some transformation to get a new value, right? You'd get a new value here. So you'd get a new value here, you'd get a new value here, you'd get a new value here, and you'd go on throughout this process to get some specific output. And so this process of calculating it as we move along, this signal propagation, where the signal goes from input layers towards the output layer, is the forward propagation. And so this, we've just said that these are just like addition and multiplication of numbers, right? So you're either adding, you're multiplying, and you're applying some specific function to just get another number, right? This is just going to be another number, this is just going to be another number, and this is just going to be another number as well. But this is the output, right? So in your case, the price of the sales price that you're predicting for maybe a day, maybe a month, maybe for next year, right? And so our prediction might be off, will probably be off, right? Especially since we start off with either assigning every number to 0 or assigning every number that this connection has with a random value. The output of this, the output that we get here, will be off by some point, right? So if you predict that you're gonna make a sale of, let's say, $1,200 over the period of next month, and the actual value in your test set actually said that there was a sale of only like $900, you're off. Your prediction was off by $300, right? So that's the error that the model that's the error that the model has, right? So that's the loss or the residual. There are multiple terms for this specific output. And so what we try to do is actually minimize this error, right? We don't want to be $300 off. We want to be as accurate as possible, especially considering that the cell amount is actually small, right? So 300 means we're 1/4 off of the actual value, which is quite a significant number. So what back propagation it does is simply from a high level overview is it goes back in time to adjust those weights, to adjust the numbers here inside of our architecture to actually minimize the loss, right? To minimize that $300, right? So it goes on until it minimizes it to an acceptable level, right? So we can be like, we can say, okay, we're okay with being off with just like maybe $10, $20, but $300 is not acceptable, right? So it would go back, it would adjust the numbers that are here until it gets that acceptable value. So that is what the back propagation step is and the forward propagation step is. So there is this circular loop that is happening here, and during that circular loop, the specific numbers that are here, here, and in almost every connection is actually updated if we have a fully connected neural network and are not tuning other parameters. Okay, so yeah, there's this back propagation that you can look at. Yeah, and so gradient descent. What gradient descent is I think we can go into this in a bit more detail because it's really important. So we can separate this into two, right? So we can see the term exactly as it is. So it is used to minimize the errors between the predicted and the actual results in the loop that we saw in the previous slide. But just separating gradient and descent. So what gradient is just the rate of inclination of a slope, right? Or how steep a slope is at some point in time. And what descent is, it means like just going down, or the act of moving downwards. So there isn't any slide that properly describes this. Okay, yeah. So if we take a linear model with y equals mx plus b, and we're trying to find the least of y, which means like the closest value of what we're trying to predict, we need to find the best values of m and b, right? So if we had a line, it would be this gradient descent would be slowly adjusting those, slowly adjusting the line over the data points that we have spread over, so that we get those perfect m and b values. So we get the perfect slope value and the perfect y-intercept value for our prediction. Yeah, so you can just think of this to allow us to minimize the errors between the predicted and actual results. And you can look into this video later on, right? Okay, so maybe if there are questions, I think I've talked too much, and let's yeah, so yeah, definitely keep the chat going. I feel like people are answering the questions, so this is good. If I say something that does not make sense, feel free to stop me midway. Okay, so, and activation functions, right? So let's zoom out and see only a one neuron architecture where we have specific inputs, where we have the weights that are assigned to the connections, and we have the outputs, right? And so we talked about having this function over the connection of neurons that make up specific layers of our architecture, right? So what is this function? And this function is an activation function. And what it does is, just like its name, it decides whether a neuron is activated or not. right? So there are many types of activation functions, but so it would allow us to decide whether or not or what type of relationship it's going to have over the output and over the next upcoming connections, right? So it might have a negative connection, it might not fire at all, or it might have a really positive impact on the output of what's going to happen, right? So there are sigmoid, ReLU, ReLU, and there are multiple types of activation functions that we can use. And I believe this blog gives a good dive into the activation functions that you can use when building your neural network architecture. So if we take sigmoid, for example, it just maps, for example, like this, if we take the weighted sum of, let's say this x1 is 100, this is 200, this is 300. So the weighted sum would be, and if we had, okay, just around, and if we had one assigned for each of this, so it would be 100 plus 200 plus 300, so 600. 600 would go into this, but 600 is a huge explosive numbers, and especially when we also increase the number of parameters, we need a specific range, just like standardization and normalization help. When we're building machine learning models, we need to standardize that. So sigmoid, ReLU, they give us this mapping where they reduce the range of the specific data point that we have here to help the performance of our algorithm, right? So, and the other ones, so the next thing we're going to look at is the error or loss functions. And this again are just another functions that are used to compute the error. So in the process of where we saw like here, in the process of forward propagation and backward propagation, the example, what was the example that we saw? Yeah, we saw the price of source, right? So we were off by $300, and so that was an error, right? We calculated the error where we were $300 off by just subtracting the predicted value from the actual value that we got. But and there are a lot of costs. There are a lot of error and loss functions. For example, we can take the mean absolute error just to start off with, which would be very easy, especially for a regression problem, where we take the error. So the error would be the predicted value minus the actual value, and you'd take the absolute value of it. And because you have multiple data points, and it is not just a single data point, you'd take the mean of it, hence the name mean absolute error. And so there are multiple errors that you can use, the root mean square error. Yeah, you can look into the different loss functions that exist, and this blog will help you understand that more. So optimization functions. Again, I know we're seeing a lot of functions, and yeah, deep learning is something that takes years, and especially even people who want to pursue the track of machine learning, of course, you'd have to know it. But it's knowing at least the details, the high overview, the overview of deep learning is useful for everyone, whether you're going into the data engineering track or the Web3 track. Yeah, but like, don't get overwhelmed, especially if there are people who are really new to this concepts. I know we're mentioning lots of functions, but yeah, the slide will be shared, and yeah, this will give you a good overview of the things you actually need to know on a high level. So optimization functions. So you can just think of the optimization functions as sort of like the cousins of this loss functions. And so they're the way the weights are in neural networks are modified. And like, so in this forward backward propagation step loop that we do, there needs to be a way that we adjust the weights that we measured, right? There needs to be a way we adjust those numbers, and the specific optimization function that you use will actually have an impact on how those weights are updated. And depending on the type of problem that you're trying to solve, you're going to have to choose a specific optimization function. I believe Adam and Adagrad were really popular, but yeah, you can read this blog for further clarification. Okay, so yeah, we've talked about the three pillars, which were the forward propagation, the backward propagation, and the gradient descent, right? And gradient descent was just another type of optimization function. And you see the list of other optimization functions, the modified type of gradient descent, which is a stochastic gradient descent. Yeah, and just read more about this. But these are very critical components of a neural network model, right? So we have activation functions which decide whether or not a neuron is activated. So it would be as if a neuron in our brain would be activated for some case and would not be activated for one case, right? And the error or loss, which is used for the punishment of the model, and which really helps, which shows us how off our model is, and the optimization functions, which are how the weights then during that backward propagation step that we saw, the weights actually become updated. So hyperparameters in neural networks. So what hyperparameters are parameters which are actually outside of our model. So we saw in the, I think we can just go here. Yeah, we saw this, the weights here. The weights here are the parameters of our model, right? They're actually parts of the model itself. But there are hyperparameters which which are not actually part of the model, but actually help the learning process. And these are three hyperparameters: the epoch, the batch size, and the learning rate. So what the epoch is, it is the number of times the algorithm runs on the whole training data set, right? So if you have, let's say, 1,000 rows, one epoch would be one forward propagation and one backward propagation, right? So you have those 1,000 rows that are, let's go back to the slide. So yeah, you have 1,000 rows with, let's say, 4 columns. So when those 1,000 rows that you're using to train your model go into the model once, and when they back propagate once to actually fine tune all of the inner parameters of the model, that is one epoch. And you don't usually just do one, you don't just go once back and forth. This is a circular loop that happens for depending on your use case and depending on how the model is being optimized. This forward and backward, one step of forward and backward propagation is called a single epoch. And the batch size or batch, it denotes the number of samples to be taken for updating the model parameters. So if you have a large amount of data set, you're not gonna feed it all in at once. You're going to feed it in a bunch of batches. And so you're going to take a couple of samples and you're going to feed that into it. And the model parameters are going to be updated on all those batches until you have what's the word for it? Yeah, until you've gone through the entire data set at least once. So for one epoch, so you use batches to actually map performance. And the learning rate, it's also another hyperparameter that provides the model a scale of how much the model weights should be updated, right? So you're trying to minimize the error. You're trying to minimize how off your prediction is. And so what the learning rate does is it's so for example, if you have a large number for your learning rate, it's going to update the parameters really by a huge amount, right? So you can take I think maybe having learning rate image search. Yeah, so I guess we can take a look at this. How do you maximize? Where is it? Okay, so I think you can all see my screen. So yeah, if you have a small learning rate requires, yeah, so it's, if this is your cost function, like if this is the how off you are or the error of your model, you want it to be as small as possible, right? So you want to get to this minimum point. But if you set your learning rate so small, like it is going to move really slowly and it's going to take a lot of time for your model to actually reach the smallest error point, right? So the minimum point. But if it's too high, like let's say you start off here, but if your learning rate is too high, you might never actually get to this low point, right? It might just bounce up and forwards, like, so its learning rate is too much, it misses it, and the weights are just way off again, and it goes on to just explode up and up, and you might really be missing the error. So an optimal learning rate would go down like this. Some of the optimization functions actually handle how this learning rate happens, how this cost minimization actually happens itself. So that's definitely something to look into over on the optimization section as well. Okay, so these are 3 hyperparameters in neural networks to look out for. Yeah, and yeah, so we're gonna have an overview on what a TensorFlow model is. But let's first see the 5-step model lifecycle. So when you're building a neural network, or when you're building a deep learning model, you go through these 5 steps. So you first define the model, you compile it, you fit it, you make predictions, and you evaluate it. This isn't necessarily just for neural network architectures, but also a model lifecycle that is known for modeling both datasets and any algorithms. So what is it when we say defining the model, right? So defining the model, it means selecting the type of model you actually need, and then choosing the architecture or the network topology. So I think let me flow LSTM. There is this time series forecasting that you should go over. I think this is it. Okay. Yeah. So there is this series forecasting that TensorFlow provides. For those that are not familiar, we've more or less seen what a neural network architecture is, but if you now go on to actually think about implementing a neural network architecture on your own, starting from scratch, it is gonna be painful. Like you need to be really good at programming. You really need to be good at understanding the mathematics behind this neural network architectures. And so what TensorFlow does is it is a framework. I think we can get it's a deep learning framework. It would give you the great machine learning. yeah, it's an end-to-end machine learning platform. Technically, it provides a lot of things. It allows you to tune your parameters. There is TensorBoard. There are many things that we can go over maybe at another session. But for our case now, it is a deep learning framework that we are going to be using to build our neural network architecture. So there are also other deep learning there are other also deep learning frameworks that you can look into. There is PyTorch, which I believe was by Facebook. There was also one by Microsoft. Yeah, but it is just one framework that we're going to use. So yeah, over on this life cycle of the model. So on this time series forecasting, let's go over I believe you've gone over the data pre-processing and EDA steps on previous sessions. So let's go over to the recurrent neural networks side. So what we've been looking at are terms that are consistent over deep learning, right? So everything that we've seen this far, this optimization functions, loss functions, error, these are general terms that you're going to use. But there are various flavors and different types of deep learning and neural network architectures, right? There is convolutional neural network, which is usually used for image processing, where you'd take specific pixel samples and pass them through the architecture. For example, in let's say a digit classification task. But for a time series data set, using a recurrent neural network is best, because normally your deep learning architecture, like we've seen, where's the slide? Yeah, okay. So in a normal neural network architecture, you can see here, you can usually spot the problem, right? So if we're trying to predict some data which has some relation based on the past data, it's really impossible, right? We can simply do a time shift where we take features of this current date, set the label to the next date's specific value, and using that time shift, we can simply predict. But that type of relationship, we're not really taking into consideration previous states that are actually happening, and that's what recurrent neural networks actually do. They consider the previous states of our model, right? And what this uses is an LSTM model, which is a long short-term memory model, which is just a type of neural network, which is just a type of RNN. Yeah, so let's just go over the definition of the model itself, right? So we could guess how just imagining it was really cumbersome. I think rather than imagining it, if someone maybe can tell us one approach, if they can think of how to actually start off and code a neural network architecture. Like one approach that you'd maybe think of to building things from scratch. Okay, actually, there's just 10 minutes left, so let me go on. Yeah. So what this does is it just provides us this great wrapper that you see here, right? So this right here is like an entire model. We've just created an entire model just by this line, and that specific flavor of that neural network architecture, right? So what Sequential does is just it creates this sort of array where we could add those layers that we saw here. So these layers can be actually added. And what this TF-Keras layers LSTM is doing is it's adding that sort of flavored layer of recurrent, that flavored layer of the neural network that we talked about, right? So it's just, you can think of this as just a normal layer, but it's a bit flavored to work on time series, to work on NLP, where recognition, where the output actually depends on previous on the previous state, right? So for example, like when we're typing an email, and we're trying to the Gmail itself tries to predict what we're about to type next. It doesn't just take into consideration the previous word that we wrote. It takes into consideration the entire sentence, or the entire context of the entire message that we had, right? And so that is just what it's doing, and it is stating that there are 32 units, which are the perceptrons and the return sequences, which is true, which means that each iteration is like the sequences for like, so okay, then going back to the time series task at hand, if you're going to predict the next 6 days of prices, you might have a window of the previous months, right? So you might be using data of each daily data of the past months to predict the next 6 days of sales that you're going to have. And so you want to use each of these dates recurrently to actually predict the upcoming 6 days. Yeah, and what this is doing is just adding the output layer. So this output layer in this case would be a single Y1 here. So it is predicting for one time step, not multiple time steps at this moment, but definitely this article goes down to, which one was it? Yeah, so this article goes down to go on and predict on multiple time steps as well. Yeah, so we would have this inputs where at time step 0, we'd have specific inputs, we'd fit it in that model, and we'd have that prediction of the next time step, right? And when I'm saying time step, it's not dependent. It might be daily. You might be working on daily data, hourly data. You might be working on daily data, hourly data, daily data. It doesn't matter. So over the next time step. Yeah. So after definition of the model, what's the? Yeah. So just like this life cycles of the models really should be internalized, right? Because they're the process that we follow when we're building our models, right? So we have defined our model, which means we have defined the architecture. And so the next process would be the compilation process, right? So we compile the model, which is the compile and fit here in this case. Compile and fit, right? So when you're compiling the model, you're setting multiple parameters. So this compilation and fitting process are actually separate. We'll see this 2 processes together separately. So what early stopping is just, it is telling it to, so like when our loss, depending on how much we are actually training the neural network, it might actually find that minimum value, the minimum loss, the global minimum of the error, but it might then go on to actually adjust and be worse. So early stopping actually stops the model from performing bad. But yeah, so this compilation process is it is setting the loss function. In this case, it is using the mean square error that we've talked about. Yeah, which is just taking the error, predicted value minus the actual value, and squaring that error and taking the mean of it. And this really explodes the loss if we actually want to penalize our model really bad. And this optimizer, yeah, it's using the Adam optimizer, and this metrics, not completely sure of, yeah, but it's using the mean absolute error, probably something similar to the loss, where it's using to probably optimize the model parameters, right? So that's the compilation process that we follow. And then we go on to fit our model or train our model, right? And in that case, we just provide the training set. We specify the epochs. In this case, it's 20. We've said one single epoch is just one iteration of the data set where it goes from where it forward propagates and then backward propagates. So we set that epoch, we set the validation data. Probably that's what the metrics is here for. And you can also pass, TensorFlow allows us to pass callbacks, which are specific calls we make after some task is done. So this early stopping would stop our model from training if the so this patience too, so it would stop if our model actually went through 2 more iterations of the epoch, and its performance, its mean squared error was actually getting worse, right? So if, let's say, we started off being $300 off, right? And then we went on to be $200 off. We went on to be $50 off. And then we went on to be $10 off. But then if after that we started being $20 off, and then we went on to be $80 off, that means our model really has started getting worse. And that tuning of the parameters are now actually getting bad. So so that's what this one does. And so we compile the model and we fit the model, right? So yeah, just fitting the model, we go on and train. It's just training the model parameter. So, and the next step would then be to make predictions on the test data. But I guess this process is actually doing both. So it's also taking the validation data, and we're actually getting that evaluation right at the moment. So you can have, it depends on how you actually split up your data. You can have a train test validation split, or you can just have a training and validation split. But it's usually the case where you'd use the training data, the testing data, to actually back propagate and update the weights. And then you'd have the validation data to go back and update the weights, and you'd then have the test data again outside at the end to make the predictions and actually go on to evaluate the model. And so the evaluation process, and so right, where is it? And so this model.evaluate should, so we get so this loss means that error or that residual that we talked about, that we want to minimize, right? And we have a mean absolute error of this. This verbose equals 0, I believe, shows the final step. So you can change this verbose variable and see at which steps. Now you can set it, I believe, to 1 to see each of the epochs, that each of the forward and backward propagation steps, and see how our loss actually either increased or decreased through time. And you would iterate through this processes to just build your model, right? I think that's it. But I think since we've seen these processes, if does anyone have questions or definitely sounds like an interesting conversation that you've had. We can, I'm sorry about that. One moment. Yeah. Okay, so if no one has questions, I think I can go over the slide one more time so that we've seen a little bit of the code. Definitely that time series notebook. Okay, yeah, to this.
Hello?
Hello.
Can you hear me?
Yes, yes, I can hear you.
Okay. Once could you elaborate us the how to use a hybrid algorithm? For example, when we deal with some problem, we can use a single algorithm. Also, for sake of performance or other advantage, we can propose to make hybrid algorithm or to use two or more algorithms. So how can we integrate those two algorithms, and at what or at which life cycle could start this integration?
Okay, so that would definitely be in the definition of the model, right? Depending on your use case. Of course, like hybrid algorithms are becoming really popular and they've really become performance. So depending on the type of scenario, maybe having like a convolutional neural network at the beginning of your model, or at the beginning of the definition of your model, at the beginning of your model, and then going on to integrate maybe RNNs, would maybe be may turn out to be a better solution, and you might have a better performance model. But yeah, it definitely, depending on your use case and depending on the experimentation, it would all depend. And so it would happen on the definition part of the life cycle.
Okay, thank you.
Okay. Mohammed?
Can you hear me?
Yes, I can hear you.
Since it's my first time to deploy a deep learning algorithm, where I could find some starter code where I start deploying or helping me to deploy a deep learning algorithm.
Okay, so I think I'm sharing it again. This code, like, it does time series classification like properly. So if it definitely might take time. It's a long code base, but that's this tutorial from TensorFlow is really all you need to actually complete your forecasting model for this task, right? But definitely some of the terms we are going to take time to internalize. I'm going to go over the slides one more time really quickly for like 5 minutes or so, but there are resources that are linked here. I think the slide is shared, or if it's not shared, I can share it here as well. Okay, yeah, it's shared. Everyone has access already. So yeah, I'll definitely make sure to add more resources here, and also on the challenge document. But this TensorFlow code will get you up and running. And when it comes to deployment, yeah, I think we can share also one more resource on deployment, but deployment won't be that difficult.
Okay.
But this will get you the model that you need.
Thank you.
Okay, so I think let me just present and go back to it. Let's have a slideshow. Yeah. So again, why deep learning? All the machine learning algorithms plateau when some data amount is reached. Deep learning does not. The more data you have, the better. Practical applications, virtual assistants, entertainment, fake news detection, and so on. So what are neural networks? So the neural network architecture that is the basis of our deep learning is based on our biological neural network architecture as well. So which are just neurons. This are the basis. This is what a neural network architecture looks like. It has specific layers, and LSTM was just a different flavor of this layer. I didn't want to get into the intricacies of that, but you can just think of it as like maybe just a bit modified version of this, right? So you have layers, you have neurons, aka perceptrons, you have inputs, you have a specific output. That's it. And there are specific numbers that are here. This is, and yeah, each of this is just specific numbers, right? And this is a weighted sum of the prior connections. And I think these resources are good. Yeah. What is deep learning? We've gone through it. Yeah, the initial layers understand low-level details. As we move on into upcoming layers, they go on to detect better features until we reach our output layer. Yeah, deep learning is just a subset of machine learning. It really uses this feature extraction process, cumbersome process of machine learning. And so that's one of the reasons deep learning is really useful. Yeah, and it has been really booming because of this reasons. The data growth, the hardware advancement, the cloud computing, and the AI boom. What were the three pillars of deep learning? Forward propagation and backward propagation. This is like the core of everything that we've talked about, right? This loop of numbers being updated, right? From the input, it goes into towards the output, it gets some value, and then it goes back. It goes backwards through the network to actually update the numbers that we have. So the weights that we have, and this updating of the weights leads to updating of the weighted sum of the neurons, and depending on the specific activation function, it would then go on to have specific values, right? And so this shows the calculus. Gradient descent is just an optimization algorithm, but the most important optimization algorithm, which is used to train machine learning models and allows us to minimize errors between predicted and actual results. Yeah, it just minimizes the errors. Yeah, we took a linear model as an example previously, so I'm not gonna get deep into that. There is this video, and we have talked about activation functions, which decide whether or not our neurons are activated or not, computing the weighted sum of the previous connections. Yeah, different types of activation functions. There is the error or the loss functions. We've talked about the mean absolute error, but you can definitely look into more loss functions. I guess there's the Hubbard loss function on the notebook that was shared on the Google Drive, which I believe is better for time series analysis, but definitely look at, like, don't just look at a single type of activation function. Like, we want you to experiment as much as possible. So use multiple activation functions, like report on why you chose that specific activation function, why you chose that specific error or loss function, and what if you have actually experimented on and tried different functions and what the results of those functions were. Yeah, experiment with the optimization functions. Sorry. Yeah, and just these are the critical components: the activation functions, the error or loss function, and the optimization functions. And we've also talked about the specific hyperparameters, which are parameters outside of the neural network, which allow us to tune the learning process. And we've talked about the life cycles of the model. So I think let me add the resource here as well. Yeah, and I'll definitely keep updating this. For those who are going to be joining the machine learning track, definitely this is the best way to start, and this is the one of the best projects that you can do. Yeah, and really, I guess, work on this, and I'm expecting to see really wonderful works. Yeah, and typically, I believe, yeah, if you have previous machine learning experience, so you can, those who have prior experience, you just don't have to follow that. You can, yeah, you can work on really complicated architectures. Yeah, and looking forward to see the work. So this was just an introduction or a revision to people who had prior experience. Yeah, so I think that's it from my end. If anyone doesn't have any questions, we can end the recording here. Stop recording.